Hello there, I'm Vahid, and I'm here with you to solve another data structure algorithm questions from Leetcode. The question that I've picked for you today is question number 96, and we need to find the number of unique binary search trees that is possible. So let's see the details of the question. Given an integer n, return the number of structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. So what's a binary search tree? A binary search tree is a tree that has at most two children, one child at its left side and one child at its right side, and the value of all the elements on the left side of the tree should be smaller than the value of the root, and the value of all the elements on the right side of the tree should be bigger than the value of the node itself. Okay, now here, as an example, we have for input n, which is equal to 3, we have 5 inputs. So these are 5 unique possible binary search trees that we can have for 3. And then for input 1, there would be only one element, one possible unique binary search tree. So for only n equal to 1, the only possible solution would be this. For n equal to 2, we could have this one. 1 is the root, so 2 would be on this right side. And for 2, have 1 on its left side. For 3, we'll have the elements that are shown here. So something about binary search trees is that a lot of the time we tend to use recursion for solving this question. So you need to keep that in mind. And to use recursion, you should usually find like a base case scenario where you already know the answer. Here it could be this one, potentially, n equal to 1. And then you need to somehow break down the harder questions into simpler solutions. In other ways, you need to follow divide and conquer approach for solving these kind of algorithm questions. So we have this solution for 1, this solution for 2, and we have these for the scenario where n is equal to 3. Something that can be noticed is if you look at this specific case where 1 is root, we have elements 2 and 3, and we have 2 different solutions for that. So in other words, you can say that if we pick 1 as a root element, then we have to somehow find all the subsequent scenarios where 2 and 3 will make another binary search tree. So in other ways, we can say this would be unique binary search tree of 2. And that's two possible scenarios. So we can cover these 2. If we pick 2, well, we would only be left with one scenario because 1 would be smaller, so it'd have to go on the left side. So we could say this would be a unique binary search tree of 1. So I'm just going to show you that U of 1. And 3 would be on the right side, so this will also be a U of 1. Okay? Now, if we pick 3, it's the opposite of scenario where 1 is picked to be the root. So it will be on this left side, and we'll have all the unique binary search trees of 2. Combining all of these, it would be 2 plus 1 plus 2, which will be 5. So we're kind of getting close to finding a formula that works for finding all of these unique binary search trees. And what I mean by that, for example, if I use n is equal to 4, it would be one scenario where we have 1. So everything will be bigger than 1, so we will have u of 3. If you pick 2 to be the root node, we'll have u of 1. because 1 would only go on the left side, and then we will have a u of 2. 3 and 4 would be on the right side. 3 would be kind of similar. The difference is 1 and 2 would be on the left side, so it would be u of 2 plus u of 1, which is like for number 4. And if you have 4, it would be similar to 1. Difference is it would be a u of 3 on the left side. So giving these in mind, the number of solutions for n is equal to 4 would be 5 for this one. For 2, we'd have 1 multiplied by u of 2, which is 2 different scenarios. This one would be similar. It would be 2 multiplied by 1 plus this one would be 5 different scenarios. So in total, we'll have 14 scenarios. 14 here, we have 2 here, we have 1 here, and we have 5 here. To make sure that they got this correct, you can do this trick. So I'm just going to return 0. I'm going to create some test cases here. I'm going to start with 1. So our inputs are 1 all the way to 19. So we have 1. This would be 2. This would be 3. This would be 4. And this would be, let's say, 19. I'm just trying to make sure that they've got the correct solution for the scenario where n is equal to 4, and I want to make sure that that's 14. Oh, we're missing this, sorry. Missing a curly bracket. All right, so that's 1, this is 2, 3 is 5, 4 is 14. And for 19, we have a lot of numbers. Over 1 million. Anyways, so it looks like we got the algorithm correct. So knowing that in mind, what we're going to do is we're going to try to solve this first by using recursion. Recursion is quite easy to understand, and it's quite easy to implement and write. Usually, it's not like the most efficient solution, but that's okay for this case. So we're going to say if n is, I have some base cases. If n is equal to 0, I'm going to return 1. Now, let's come back here. And what kind of formula can be devised here? It looks like we're starting from 1 and going all the way to n. We are saying the result would be equal to u of I in this range, u of I, n minus I multiplied by u of I. And this would be plus equal. It would be something like this. Does that contain all the cases here? So next, we would go and we would say that I is equal to 2. So we have 3 minus 1. Okay, let me write it down here. I think we need to optimize it, but we're never going to know until we actually run it. So we're going to say 1 all the way to n. We're going to define result to be 0. And the result plus equal num3s of n minus I multiplied by I. return result. Oh, sorry. Return result. Give the average Stack Overflow. Let's see, let's get back to this algorithm here. So here, for example, we have n minus I, which will be u of 1 multiplied by 1, and then we'll have I equal to 2, that would be 0, and 2. That wouldn't work actually. This should be I minus 1, guys. Now, if we take that into consideration, yeah, that would work. That would work. So, for example, for 3, at each iteration, we're going to say n minus I, so it would be unique minus h3 of 2 multiplied by 0. We can set 0 to be 1, the same as unique minus h3 of 1. And for here, it would be 2, so it would be 3 minus 2 multiplied by 2 minus 1, which is going to be this one. And for here, it would be n minus I. So yeah, that should work. Let's try this. Fantastic. So it would be a very simple recursive solution. I think we can definitely modify this as well. Yeah, awesome. Yeah, it's kind of slow, the approach that we used. And it's because we're kind of like calculating this number of trees for the same numbers probably a couple of times. And we can definitely improve that. So we can add n equal 1, be return 1. This is one simpler approach to improve it. But what we can do is we can actually use an array where we keep record of all the unique binary search trees that we have calculated all the way towards n. So to do that, we need to create an array. So we're going to say val results. It's called int array. And at most, we'll have 20 elements here. Initiate them with value of 1 for 0 and 1. And say if results of n is bigger than actually let me do it this way. So I'm gonna say if n is smaller or equal to 1, then return results of n. Otherwise, calculate this one. Okay, this is not really making use of this, making use of the previous calculations, and we have an issue here. Results. Oh, sorry, this should be return again. Sorry. This should be return again. Or if results with n is bigger than 1, because we know that from 1 onwards, the value of all the unique binary search trees will be more than 1. We had it for 2, which was 2, for 3 it was 5, and for 4 it was 14. So in this case, you need to return results. And I'm going to get rid of this one, this variable that you use here, results. And we're going to use results n, and we're going to do it this way. So because we initiated everything to be 1, we're just going to change it to 0 so that our sum is calculated correctly within this loop for each n. And we also check if the value of n is 0 or 1, you're going to return whatever we have already, you're going to return 1, which I've already saved in this results. Otherwise, if it's more than 1, which means that we have already calculated it, just use the calculation and don't go through this again. I think this looks, yeah, this looks really good and should not have any problems. Yes, it's complaining about this, so it should be results index n. Let's try to submit it. Awesome. So we actually beat 100% of all previous submissions. I'm very satisfied with the solution. Really happy with it. And let's say we compare it to the previous one, which only bit like 5% of the submitted solutions in Kotlin. So this is pretty good. The other thing is we kind of use some dynamic programming approaches here. So we save the result of the previous calculated submissions. Amazing. Now, one other improvement that we can do here is we can try to change this into an iterative approach instead of a recursive approach. So to do that, we need to change a couple of things in here. So I'm going to move this here. So this wouldn't be filled anymore. It would be just a variable within the function. And I'm not going to initiate it with 1. I'm just going to initiate it with 0. And I'm going to say that results 0 is equal to 1. I'm going to do the same for results of 1. And I think just said we're going to calculate. So we have started with results 0 and results 1. So we're going to start going all the way to results n. So the next one would be 2. So in this loop, we're going to change that to 2. And for this one, we're going to start again. We're going to use a similar algorithm, similar to the previous one. We're going to say from j to, not to n, all the way to I. So if n is, for example, 5, at this step, we need to calculate the unique number of binary search trees for 2. So once we calculate that, we can go to 3, and then to 4, and then to 5, all the way to n. For that purpose, this would be I. It would be I minus j, and this would be j minus 1. And we're going to return the results n. That's our last calculation in this loop. I'm going to do it this way. Let's see. Okay, it says time limit exceeded. So something has gone wrong here. Oh, and it's because I'm calling the function again. So this should be results. Should make use of the previously calculated array elements. Oh, and we're not doing it properly. Have some syntax errors. This should work. Awesome. Oh, and we don't need to create an array with size 20 anymore. We can actually just use n plus 1 because we also have 0. So if it's n is 4, then we need 5 array elements. And let's just check this very quickly. And let's submit it. Awesome. Well, not as fast as the previous solution, but this also worked pretty well. Perfect. I really love to solve tree-related questions. They're quite fun because of all the recursions and using different approaches and stuff. It makes it really fun and intriguing to solve. Thanks for being with me. I'll see you guys in the next video with another exciting algorithm questions. Take care.